Hello everyone, I am Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about pin photodiode and avalanche photodiode. So let us see the brief outline of this topic. First we will see about pin photodiode, its introduction, principle and working. And then we will discuss about avalanche photodiode, its principle and working. So first we will see the principle of pin photodiode. So here when I say pin, in pin, P stands for p-type material, N stands for n-type material, and I is intrinsic. I is intrinsic. That is why we call it as a pin diode or a pin photodiode. So a pin photodiode is nothing but a photodiode, but in the construction and the working there is a slight difference from photodiode that we are going to understand now. So this is a device used to convert light energy into electrical energy. So whenever we say a photodiode, photo is always related to light. So light energy is being converted into electrical energy. And then in reverse bias, we are going to connect this pin photodiode in reverse bias. And when the light rays are incident on the intrinsic region, I said there are three different regions. So when the light is incident on this intrinsic region, then it will produce electron hole pairs. Means it gives rise to the generation of electron hole pairs. And when these electron hole pairs are accelerated, they produce photocurrent. Why we are calling it as photocurrent? Because it is due to light. Photo is always related to light. So we call it as photocurrent. Now coming to the construction of this pin photodiode, or we may simply say it as pin diode. It consists of three layers. What are the three layers? The first one is the P layer, first layer, and the second one is the intrinsic layer, I layer, and the third one is the N, that is the N layer with proper biasing. So if you see the figure here, you can see here, this is the photodiode we have taken. Okay. And here there are three regions. So this is the first region, which is the P region. And then the second region, this is the intrinsic region, Pi. And this is the third region, N. That is why we call it as a pin diode or pin photodiode. Now coming to the P and N regions, they are heavily doped. They are heavily doped. What is doping? We have already discussed in our previous lectures. So we'll just try to see the definition of doping. Doping is a process of adding an impurity to a semiconductor. So when I take P-type semiconductor, means we have added a trivalent impurity. And when we are talking about N-type, we have added a pentavalent impurity. So heavy doping here means the concentration of impurity atoms that are added are high. Then only you say it is heavily doped. So we are taking these two regions, the P region and the N region, they are heavily doped. But the intrinsic layer is slightly larger in size than both the N-type and P-type, and it is not doped or very slightly doped. That is why we are calling it as intrinsic. Whenever we say intrinsic, intrinsic means it is pure. It is a pure semiconductor. So P-type and N-type, they are heavily doped, and they are thin regions, whereas I, intrinsic, is a pure region where there is no doping or minimum doping, and the width of the intrinsic layer is large. Now coming to the working. How does this PN diode work? Working of a PIN diode. So when the PIN diode is unbiased, unbiased means we have not connected any external supply. So when there is no external supply, what happens here is the charge carriers will flow from the N-type region to the intrinsic region. So when I say N-type region, so this is the N-type region. So when I say N-type, electrons are the majority carriers and holes are the minority. So there will be movement of electrons from N into the intrinsic region. This is because of diffusion. That is the concentration gradient we are calling. What is concentration gradient? There is a difference in the concentration of the charge carriers. Means in the N region, the concentration of electrons is high, whereas in the intrinsic region, it is less. So they move from the N side to the I region. Then the width of the depletion region. So what is a depletion region? We need to understand. When there is movement of charge carriers from N into the I, so on the N side, there will always be immobile ions, positive ions that are stuck to the crystal lattice. And in the intrinsic region, there will be negative ions. And because of this, the region that is developed is depleted of charges and it has only immobile positive and negative ions, and we call it as depletion layer. And this depletion region at the Ni junction, what is the junction we are talking about? This particular junction, N and I, where N and I meet. At this junction, what is happening? The width will be more on the N side and less on the I side. So on the N side, the width of the depletion layer is more, but it is less on the I side. What is the reason for this? For the variation in the width of the depletion layer. So the reason is N-type material is heavily doped. We have already discussed when we have taken the P-type and the N-type, they are heavily doped. So when they are heavily doped, what happens? So the movement of charge carriers is also more. So the width towards the N side is always more. So because the intrinsic layer is not doped or the doping is extremely low. So what is happening here is the charge carriers flow from N-type to the intrinsic region and the depletion layer is created. But the width of the depletion layer on both the junction, on both the sides of the Ni junction is not the same. It is more on the N side and less on the I side. Now, when we do reverse bias, when it is connected in reverse bias, what is reverse bias here? You take the P-type of the junction diode and connect it to the negative terminal of the external supply, and the N-type is connected to the positive of the external supply. So this is the positive of the external supply. This is the negative of the external supply. We have connected N to positive and we have connected P to negative. Means this is in reverse bias. Then what happens? The reverse voltage keeps on increasing. So when the reverse voltage keeps on increasing, what happens? The width of the depletion layer at the Ni junction also increases. Because what we have understood before also when we have discussed in detail about forward bias and reverse bias, we have seen very clearly why the width of the depletion layer increases in reverse bias. So here, because we have connected in reverse bias, so as more and more electrons are pulled towards the positive side and more holes are pulled onto the negative side, the width of the depletion layer increases. This is because of reverse biasing. So now this increase in width of the depletion layer will increase to an extent where the entire intrinsic layer is swept away of the free charges. Means as the depletion layer increases, the whole of the intrinsic region is swept away of the free charges. Means the whole region, intrinsic region, is now free of charge carriers, and you will call it as a depletion layer. So this particular voltage at which all the charges are swept out, we will call it as swept out voltage. And this is around -2 volts. So the voltage at which all the charge carriers are swept out from the intrinsic layer. Now we'll see the working. In the working, what we see here is we have taken the pin diode and we have connected it in reverse bias. Now when a photon of high energy is incident over the larger width of the intrinsic semiconductor layer. So what we have taken a pin diode. In the pin diode, P and N are heavily doped, I is lightly doped, but we have connected it in reverse bias, and with the reverse bias, the width of the depletion layer goes on increasing. So when the width of the depletion layer is more, on that region, when photons of high energy are incident, then what happens? Electron hole pairs are created. So whenever there is an electron that is coming out from a particular site, there is a hole that is developed. A hole is nothing but a deficiency of electrons. So they are always created in pairs. So by the energy, when we are allowing the light to fall onto the intrinsic layer, the means photons are incident. So these electron hole pairs, they are generated because of the energy that is incident on the intrinsic layer, and these mobile charges are now accelerated by the applied voltage. Now what we have done, we have connected it in reverse bias and we are keeping on increasing the reverse voltage. So because of the voltage that is applied, these electron hole pairs that are generated, they are gaining the energy and they are getting accelerated, and these accelerated charges will give rise to current. And we call it as photocurrent because it is due to light. So, and this is a linear device. Why we are calling it as a linear device? Because photocurrent is directly proportional to the incident optical power. So, as the amount of light falling on the pin diode increases, the photocurrent also increases. That is why we are calling it as a linear device. It's a proportionality. Now, what is the impact of reverse biasing? We will see here. When the pin diode is connected in reverse bias, it is used in various devices working at microwave frequencies, such as a microwave switch. So, I can simply say, when connected in reverse bias, it can behave like a switch, and that too in the microwave frequency region. And if all the charge carriers are not removed from the intrinsic layer, there may be a small current that is flowing. And if there is a small current that is left, then we cannot use it as a switch. Switch means it should be either in the off position or on position. Off means no current and on means the current flows. So here, if at all there is a small current that is flowing due to the left out charge carriers, then it cannot act as a switch and the device becomes useless. So we need to make sure that all the charges are swept out. That is why that swept out voltage is very important. Now coming to the forward bias. So when this PIN, that is pin diode, is connected in forward bias, what happens? The gradual increase in forward voltage decreases the width of the depletion layer. So this is also one important point we have to remember. So in reverse bias, when we are connected it in reverse bias and increasing the reverse voltage, the width of the depletion layer is going on increasing. But when you connect it in the forward bias, what is happening? The width goes on decreasing. So with the reduction in the width of the depletion layer, the current starts increasing. So because the width of the depletion layer is going down, the current will start flowing. So what is the impact of biasing? We have seen two biasing. One is forward biasing, what happens, and one is reverse biasing. We will just summarize what is happening in biasing. So in forward biasing, it acts as a variable resistor. Variable resistor means when the resistance varies, the current varies. No? So we know that V is equal to IR, or V upon I is a constant, and that is nothing but the resistance. So as the resistance, if the resistance increases, the current decreases. So as the resistance is lowered, the current increases. So as we are varying the resistance either by decreasing or increasing, that is a variable resistor. So in forward biasing, it acts as a variable resistor and it provides variable resistance in the circuit. And when it is in reverse bias, it is acting as a switch. Switch means on and off. It provides infinite resistance. When infinite resistance means there will be no current that is flowing. So it may be in the off condition. So in forward biasing, it acts as a variable resistor. That is the advantage of a pin diode. And when connected in reverse bias, it is acting as a switch providing infinite resistance. Now, the penetration of the photons through the layer depends on the wavelength of radiation. Whatever photons that are incident on the intrinsic layer. Now, the shorter wavelengths like the ultraviolet range, they are absorbed at the surface. While the longer wavelengths, that is the infrared, they penetrate deep into the structure. So, the wavelength of the incident radiation also matters in the prediction of photocurrent. Now coming to the characteristics of the photodiode. What are the characteristics of this pin diode or pin photodiode? So at lower frequencies, the charge carriers from the intrinsic layer can be detached easily as we have sufficient time. So at low frequencies, we have sufficient time, and because we have sufficient time, they can be detached. The charge carriers can be detached easily. Means low frequency means time factor is large, as a frequency is always inversely proportional to time. We know F is proportional to 1 by T. So if F is small, T is more. So low frequency results in large time factor. That is what we are understanding. Low frequency here means the time factor is large. And because the time factor is large, the more charge carriers can be detached very easily. And at higher frequency, so when the frequency is high, the time factor is low. Again, because of the same reason, F is inversely proportional to 1 by T. So when F is high, T will be low. So at higher frequencies, the time period is low and the charge carriers cannot be removed completely. You cannot remove the charge carriers. So it behaves as a resistor having a range between 0.1 k ohms, that is 0.1 kilo ohms to 10 kilo ohms. This is the range in which it acts as a resistor. Now coming to the applications. Applications means where all we are going to use this pin photodiode. It is used as a high voltage rectifier. We all know rectifiers, no? So which is used to rectify the current. So in a high voltage rectifier, how are we going to use this pin diode? The large width of the intrinsic layer imparts the ability to the diode to tolerate high reverse voltage. And it does not lead to the breakdown of the diode. Because the width of the depletion layer is very large, it can withstand more reverse voltage. As you increase the voltage, the breakdown does not occur so easily because of the large width of the intrinsic layer. So you can go to a very high reverse voltage. and thus rectification at high voltage can be implemented with the help of pin diode. So you can do the rectification at high voltage because it can withstand without breaking down at high voltage. Then it can also be used as a RF switch, that is radio frequency switch. So here the width of the depletion layer is comparatively more than the layers of the other layers like the P and N. So the separation between the semiconductor layers and it will be the less capacitance. The capacitance will be less. So the diode can be operated as a switch and the capacitance should be negligible. Then as a photodiode. So the main function of this pin is a photodiode, I said. It is nothing but a conversion of light into electrical current. That is with the help of the intrinsic region. And more the width of the intrinsic region, more the efficiency of the diode. So somehow you can make the photodiode in such a way that the width of the intrinsic region is more. So that the efficiency of the diode can also be increased. Then comes the attenuator and RF protection circuit. So when a pin diode is connected in forward bias, it works as a variable resistor. This we have discussed already. Okay, and it can also be used for protection of RF. RF here is the radio frequency circuit from high current. Whenever there is a high current that is flowing through the circuit, with the help of this, because the pin diode acts as a resistor, by increasing the resistance you can lower the current. So we can protect it without the circuit getting damaged. So when the forward bias is increased, the resistance decreases suddenly. Thus it can be used as an attenuator. So in attenuation, what we have to do, when we increase the forward bias, the resistance will decrease suddenly and it will behave as an attenuator. Now coming to the advantages. What are the advantages of pin diode? So it has a high reverse breakdown voltage. The reverse breakdown voltage is very high. I told you what is the reason? The width of the depletion layer. It is because of the large intrinsic layer we have taken. So it imparts the ability of high reverse breakdown. Means the reverse breakdown or the breakdown will happen at a very high reverse voltage. So it is suitable for protection of circuits from large current. So whenever there is a large current flowing through the circuit and when you use a pin diode, it will act as a variable resistor and it will protect the circuit from damage by withstanding high reverse voltages. Then comes the capacitance. So the width of the intrinsic layer is large, due to which the capacitance of the diode is low. So how does this matter? How the width of the depletion layer affects the capacitance? Because the capacitance is inversely proportional to the distance between the electrodes. Whenever we write the formula for a capacitance C is equal to epsilon naught AK by D. This is the general formula we use for the capacitance. So here D is the distance between the plates and C is the capacitance. So what is the relation between the two? Here, as the distance between the plates increases, the capacitance decreases. They are inversely proportional. So capacitance is inversely proportional to the distance between the electrodes. So more the distance, more the width of the depletion layer, less the capacitance. Then comes the photodetection. What is photodetection? Because of the large width of the intrinsic layer, the photons striking the surface will be more. So more the surface area, more the number of photons that are striking the area. So as more and more photons strike the area, more and more electron hole pairs are generated. So as the width of the layer is more, the area that is available for the photons to be incident is more, because we are allowing the photons to be incident on the intrinsic layer. And then when the photons are incident on the intrinsic layer, there are whole electron hole pairs that are generated, and with the increase in the number of photons, the generation of the electron hole pairs also will increase. So when there are electron hole pairs that are created, it gives rise to photocurrent. There will be more current. And the pin diode helps to achieve improved photo detection. So it will help in detecting the light. Now coming to the disadvantages. What are the disadvantages of the pin diode? High reverse recovery time. So the recovery time is very high. Okay. So the pin diode has high reverse recovery time, due to which the power losses are significant. There will be large power loss because the recovery time is very high. Now, what are the features? What we are seeing here is most common photodiode, pin diode we are using is the silicon. It is popular as a radiation detector, and it acts in the wavelength range of 0.4 to 1 micrometer. And it has the following features. Whatever we are using here, pin diode, it has high quantum efficiency. It is small in size and good linearity of response. And the bandwidth is very large, and simple biasing requirements. The biasing requirements are also very simple, and the cost is also less. So because of all these characteristics, it is used popularly as a radiation detector. Now coming to the avalanche photodiode. So what is an avalanche photodiode? We will first see the construction and then the working. So why we are calling it as avalanche photodiode is because of the extra performance. The extra performance it offers when compared to the pin diode or the other diodes, you call it as avalanche photodiode. And these avalanche photodiodes are used to change the signals. Most of the time they are used to change the signals from optical to electrical, from light to electrical. And they can be operated in high reverse bias. These avalanche photodiodes can be operated in very high reverse bias. Now coming to the symbol we are going to use for avalanche photodiode. It is similar to the Zener diode. We have already discussed about Zener diode and its symbol. So what is the symbol for this avalanche photodiode is, we have a triangle and a vertical line which is bent at both the ends. This is how it is bent. And this side we say it is positive, this is negative. So this is connected to the anode and this is connected to the cathode. So this is what we have we use as a symbol for the avalanche photodiode in any circuit. Now we'll see the construction. The construction of a pin photodiode and avalanche photodiode are similar. Like we are taking different types of layers P and N and taking an intrinsic layer. So here also it is more or less similar to that of a pin diode. So this avalanche photodiode is similar to a pin diode, but it is more sophisticated. So that is why it is very much useful when low levels of light are to be detected. Even the intensity of the light is very less. This can be used as a detector. The avalanche photodiode can be used. So let us see the different regions. So what are the different regions that are there in the avalanche photodiode? So the first one is the thin and heavily doped N plus region. So if you see the figure here, this is the N plus region. This gray area which we are seeing, this is the N plus region and this is thin. So heavy doping always results in thin layers. So this is thin and it is also heavily doped. Heavily doped means the concentration of impurity atoms that are added are more. That is why we call it as heavily doped, and it is thin region. Then the second region we have is the p-type. So the p-type. If you see in the figure here, this peach color area, this is the p region. This is N plus, and then you have the p region. P region is also very thin. Then we have the thick and the lightly doped. Lightly doped or pure, we say. It is the intrinsic region, which we call it as I. This is I. This is N plus, this is P, and this is I. So the I region is very lightly doped, or we call it as the intrinsic region. And because it is very lightly doped, the region is very thick. Then again you have thin, heavily doped P plus region. This is the fourth region. This is P plus. So you understood the difference between a pin diode and an avalanche photodiode. In avalanche photodiode, we had only three layers, P, I, N. P is the P layer, N layer. These two are heavily doped, and in between we had an intrinsic layer which is pure. But here what we are having an N plus layer, a P layer, an intrinsic layer, and a P plus layer. So between N and P, we are having P and I. That is the difference. We are telling that it is sophisticated. So the N plus and the P plus regions are heavily doped, and they have very low resistance. I region is very lightly doped and it is almost intrinsic. Lightly doped or almost intrinsic means pure. When I say intrinsic, it is pure. Now the P region works like the anode, and the N region acts as the cathode. So this P region will act like the anode. You see here, it acts as the anode. And the N region here acts as the cathode. This is the contact we will have for the N region, and this acts as the cathode. This is the contact we have for the P region and acts as the anode. And as compared to other photodiodes, this diode works in high reverse bias condition. So this is also connected in reverse bias, but it can withstand a very high reverse voltage. So the avalanche photodiode operates in reverse bias mode in order to increase the field in the depletion regions. So as the reverse bias is increased, the width of the depletion layer goes on increasing, and there is an electric field that is developed across the depletion region. So the N plus region is now exposed for illumination. So you see here, this is the N plus region, and you see the light is incident. This region is exposed to light. Means photons will be incident on this region. And then after the photons that are incident, we connect it in reverse bias. The width of the depletion layer widens enough to reach throughout the intrinsic layer. So as the width of the depletion layer goes on increasing, at one point of reverse bias voltage, the whole of the intrinsic layer will become depletion layer, and the absorption of photons and photogeneration takes place. So as more and more photons are incident on this N layer, so this energy is absorbed by the intrinsic layer, and then electron hole pairs are being generated. So when light penetrates through the N plus region, it gets absorbed within the extremely resistive P region. Then hole pairs, electron hole pairs are generated, and avalanche breakdown occurs mainly once the photodiode is subjected to maximum reverse voltage. So the voltage at which the breakdown of this diode occurs, we will call it as avalanche breakdown. And because of this high voltage, it enhances the electric field beyond the depletion layer. The electric field will spread beyond the depletion layer. So the electric field is maximum at the N plus side and it is minimum at the P plus side. And the drifting electrons that are arriving at the P layer experience elevated levels of electric field and they will acquire enough energy to impact ionize some of the silicon covalent bonds and release the electron hole pairs. So if you see the bonding in a silicon atom, so if you see silicon which has 4 electrons, all of them are forming covalent bonds with their neighboring atoms. This is how the bonds are formed. Now, as we are applying the reverse voltage and the light that is incident on the N plus region will generate electron hole pairs, these electrons will start drifting towards the P layer and they will experience a heavy electric field and they will acquire so much energy to ionize some of the covalent bonds. So they will try to break these bonds and make the electrons free. So when the bonds are broken, the electrons are becoming free and this phenomenon is called as impact ionization. So what is happening? The electrons that are gaining the energy, they are now capable enough to impact ionize and break the covalent bonds and release the electron pairs. And this phenomenon we are calling it as impact ionization. So when the velocity is highest, the charge carriers will collide through other atoms and produce new electron hole pairs. So as these electrons that are produced will move forward, they will come across other atoms with which they collide and then they produce new electron hole pairs. So a huge charge carriers pair, that means electron hole pairs, will result in high photocurrent. So as more and more electrons are generated, they give rise to more electron hole pair generation and that gives rise to high photocurrent. So let us understand this figure. The electron hole pairs due to the high electric field get high energy. So that is what we have seen. The electron hole pairs subjected to this high electric field, they gain high energy, kinetic energy, and they cause impact ionization and releasing even more EHP. EHP is nothing but electron hole pair. Electron hole pair. So the result of impact ionization is electron hole pairs, or this electron hole pair generation leads to avalanche of impact ionization process. So the impact ionization occurs and the multiplication is initiated by electrons. They get multiplied. One electron going and hitting the other one. Again, electron hole pairs are generated. These electron hole pairs will hit the other atoms and more electron hole pairs are generated. So the holes that are generated in the I region, they just shift or drift towards the P region and they do not take place in the multiplication process. So the multiplication is mainly due to the electrons. So a single electron entering the P layer can generate a large number of electron hole pairs which contributes to the photocurrent. So this avalanche photodiode has internal gain mechanism. So whatever is happening internally. So the electrons that have gained sufficient energy, they are creating electron hole pairs and these electrons in turn colliding with the other atoms and then creating more and more electron hole pairs. So the number of charge carriers gets multiplied in geometrical progression. And this is called avalanche effect. Why we are calling it as avalanche effect? Because the effect is very high. Because here multiplication in geometric progression is occurring. And this avalanche multiplication corresponds to quantum efficiency, which is greater than unity. Okay. And if you see one electron hole pair on an average will generate m electron hole pairs, where m is a multiplication factor. So I take one electron hole pair, that will generate not one electron hole pair, but it will generate m electron hole pairs. So this we can understand in the figure here. So here, this is the intrinsic region where the light is incident in the form of photon. So when light is incident, what we have seen, the electron and the hole pairs are being generated. This is the electron and this is the hole pair that are generated. And these electrons, when they gain sufficient energy, they come and they will hit the other atoms in the p region. So the more and more electron hole pairs are generated. So these are the electron hole pairs that are generated. Now this electron will go and hit and create more electron hole pairs. This will come and hit more electron hole pairs. So the same way, this is going and hitting and creating electron hole pairs, and this is going and hitting and creating more electron hole pairs. Again here, this will create more, and this. This is how the electron hole pair multiplication process goes on. Now coming to the characteristics of avalanche photodiode. So these avalanche photodiodes, they are highly sensitive and high speed diodes. So which use an internal gain mechanism. And that is happening because of the applied reverse voltage. We have discussed this phenomenon entirely, how this internal gain mechanism is happening inside the avalanche photodiode. And as compared to the pin photodiode, they are used to measure very low range light. So low range light can also be detected with the help of this avalanche photodiode. So they are used in applications where high sensitivity is required, like the measurement of optical distance, and also used in optical communication for long distances. Coming to the advantages, whatever the characteristics of the avalanche photodiode, they will become the advantages for using the photodiode. So what is the greatest advantage? The sensitivity range is very high. So it has high performance, quick response time because it is used in low frequency range. Then it also detects low intensity light. So we are using them to detect light at a low intensity. Then a single photon generates a huge number of charge carriers. This is what we have discussed in multiplication and production of electron hole pairs. Now coming to the disadvantages. The required operating voltage is high. It can withstand very high voltage, we thought, but for multiplication to occur, we have to operate it at a very high voltage. And then the output of the diode is not linear. So whereas in a pin diode we have seen it is linear, but here it is not linear because multiplication, and that too it happens in geometric progression. And then high range of noise. There is noise that is created because of this avalanche process. Then it is not used regularly because of low reliability. So it is not so reliable. And it uses high reverse bias for its operation. So the high reverse bias is also a problem here in operating the devices. So other applications of avalanche photodiode, it is used in laser scanners. It is used as an analyzer bridge of antennas. Used as PET scanner, wherever we are using PET scan. So these avalanche photodiodes are used. And then barcode readers to read the barcodes, and also laser microscopy in microscopic details. Wherever we are using this laser, we use avalanche photodiodes, and laser range finders to find the range or the distance between two points which are very far. And then it is also used in speed guns. So that's all for now. For any clarification or more information regarding this topic, you can refer to these two reference books. One is Semiconductor Devices, Physics and Technology by Simon Z. Mingui. And the other one is Principles of Solar Cells, LEDs and Diodes. Diodes here They have discussed about different types of diodes by Adrian Kittai, Ville Publications. You can refer to these books for more information. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.